So one last thing that I need to talk to you guys about fluids. And that is, we understood in the last lecture why the shower curtain comes back at you. Another thing that we need to look at is when you have water coming out of a faucet, that as it falls, the water gets more narrow. And just as the shower curtain used Bernoulli's equation to do this, for this, the equation of continuity handles that part. Now the equation of continuity, the conservation of flow, A1 V1 is equal to A2 V2. At the top, you're going to have to give it an initial velocity. Everything on that level is dealing with the number 1. Everything down here is dealing with the number 2. So it does have an initial velocity coming out of the faucet. Otherwise, it really wouldn't do anything. The height difference between this, let's just say, is 0.2 meters. What I want to know is, what is the velocity at the bottom and what is the area at the bottom? Now, the initial area, will make it 0.01 square meter, and I want to know what the final area is at the bottom. For this particular problem, you need to understand that obviously as the water comes out of the faucet and falls down, it's going to increase its velocity. And probably the best way to attack this problem is to use conservation of energy. You could do it with motion, but energy just seems to be the best way. The energy at 1 is equal to the energy at 2. This makes the assumption that there is no friction, the water isn't brushing up against anything, and that would be weird. So energy at 1 means that there is a kinetic energy and that there is a potential energy. At the bottom, it's all kinetic energy. So kinetic energy at 1 is equal to the potential, kinetic energy of 1 plus potential energy of 1 equals kinetic energy at 2. Kinetic energy at 1, 1/2 mv squared plus mgh equals 1/2 mv2 squared. All of these have an m term, so they cancel, and I'm left with v1 squared plus 2gh1 is equal to v2 squared, and v1 squared plus 2gh1 is equal to v2. v1, I didn't give a v1. Let's just say 1 meter per second. So 1 plus 2 times 10 times 0.2 square root gives me square root of 5, 2.23 or 2.24 meters per second. That's the velocity of the water after it has fallen a mere 20 centimeters. Now the equation of continuity takes this into consideration. The amount of water flowing through level 1 has to be the same as the amount of water flowing through level 2. If you take this into account, the new area has to equal the old area times the old velocity divided by the new velocity. So A1 0.01, V1 is 1, V2 is 2.24, and that gives me 0.0045 square meters. So it went from 1/100th of a square meter to roughly 4 to 5 thousandths of a meter in a mere 20 centimeters. And so this is why when you turn on your faucet, not so hard enough that the air is shooting through it, but when it's just one solid bit of water, that you get this tapering off, that it's wider at the top than it is at the bottom. Now other forces come into play, and that's the reason why the water breaks apart, that eventually the water gets thin enough so that the other forces, surface tension primarily, breaks the water up into droplets. Otherwise it would get thinner and thinner all the way down. And so that is that's one of the other purposes of fluids. Trying to think the biggest problem last night in lab. Trying to think. Everything was going along fine until now, what I did is I took the last problem off of the last problem set, and since it didn't have a buoyant force, we didn't have access to buoyant forces, a lot of those problems just got shifted over into the next one. If this had a mass of 500 kilograms, if it was completely out of water, that tension would equal the mg, because the sum of the forces of y is equal to 0. That is tension up minus mg down, so tension is equal to mg. And we've used that in problems like this, where there is no water bucket. It's just a mass hanging there at the end. And so this tension, which is the force that we use to work with the torques and stuff pulling down, is simply mg. But if we've got this thing suspended in water, the volume and density become important. With something like this, we need to have information about it. Let's say that it was 3,000 kilograms per cubic meter. So your initial scale would read 5,000 newtons what is T prime, and T prime is the tension in the cable once this thing is in water. To use a force diagram, you have the tension of the cable up, you have mg down, and you have the buoyant force pulling up. Those are the only three forces acting on it. Now, in all these fluid type problems, it's gonna be static. The only other question that could be asked if it wasn't static or multiple choice questions, if the sum of the forces is greater than 0, it moves up. if the sum of the forces is less than 0, it moves down. Now, for those are more like multiple choice questions. If the sum of the forces is equal to 0, it stays at the same level. And for these three situations, we learned the terms positively buoyant, negatively buoyant, and neutrally buoyant. And you should be able to know those terms. And when you sit there and you look at the term buoyant, oh, I'm dealing with a fluid, it's floating around somehow. Positively buoyant, up. Negatively buoyant, down. Neutrally buoyant, stays the same. But to figure out the new tension, obviously one can ask the question, what is this thing doing? Is it moving up, down, or staying the same? I would say in a testing situation, it's staying at the same level. There is no motion. That means the first equation coming out of the gate, and a lot of you just go, well, I don't know where to start. Well, if it's not moving, the first thing you do is write that down. And then you think to yourself, well, I've got all these forces flying around all over the place. They all have to equal 0. What forces am I dealing with? Well, I've got the buoyant force, which is up. I've got the tension, which is up. And I've got the force of gravity, which is pulling down. So positive, positive, negative. I'm looking for T prime. So mg minus fb is equal to T prime. Well, I've got m, that's 500. I'm on the planet Earth, that's 10. But buoyant force, rho v g. G is also, I know that I'm on the planet Earth, so I don't have to worry about that. V is the volume of displacement and since it's completely submerged, the volume of displacement is the total volume. The last thing is this rho. That rho is the density of fluid being displaced. Most likely it will be water. And if it's water, then that's 1,000. The one thing that I don't have yet is the volume. However, density is mass over volume. So volume is mass over density. So this equation here, mg minus rho water, mass over rho of whatever material this is. And notice how I'm distinguishing this from that by putting a little w there, times g is equal to T prime. And so that gives you the equation that we need, because now we know all of the quantities. In fact, I can do one more simplification, mg 1 minus rho w over rho is equal to T prime. M 500, G 10, 1 minus 1,000 over 3,000. Oh no, I got that right. 2 divided by 3 gives me 3,333 1/3. You can go get it. It's not yours? It's not worth it now? Okay. So that's the tension. And as a question, and one of the things that bothered me a little bit, they were like, what are the units of tension? And I'm like, it's force, newtons. Because when you look at it and you go, well, let's say for an instance, I go, well, what is tension? What are the units of tension? Well, back here, you just solved for tension is equal to mg. M is in kilograms, gravity is in meters per second per second. Those two together give you newtons. So it's a lot of times I don't memorize what goes with what units, but what I do know is what are the expressions. And what we'll do is tomorrow at the tutorial, 1 o'clock in Bishop, is we'll go over a few more of these on the problem set. But now we have to move on to something else. Oscillations and pendulums.
Quick question, Dr.
Yes.
On the last page, when you had something about volume, what was the rest? I didn't get to finish.
Is what?
I didn't get to finish writing the rest of the last page. It was something about volume. Okay, I see it. Thank you.
You're welcome. Give it a second. I'll drink some coffee. Get better. Yes. Mm-hmm. Yes, thank you. Any what? I'll give you the basics. Like, it'll be water, air, helium, aluminum, stuff like that. If I ask for a density, obviously it'll be like rebellium, whatever I deem it necessary. But I'll give you all the densities that whenever I think of it. And water is just, I'll put water on it, but everybody in their right mind should know it's 1,000 kilograms per cubic meter. Oh, which brings up another thing. When in doubt, kilograms, meters, seconds. End of discussion. But what about milliliters? Kilograms, meters, seconds. But how about cubic centimeters? Kilograms, meters, seconds. And all those variants. Cubic meters. I got this last night, which caused me to just go, my brain just derped out for about 30 seconds. Cubic liter. Cubic liter. Fried my brain for about 30 seconds. The brain had to reboot. Liter is a volume. Cubing a volume is weird. Don't do that. Or as my niece would say, don't do that. That's bad. So don't do that. A lot of you are laughing, but a lot of you were writing cubic liters last night. So, also, one of my students, in determining the mass of the object, said that it was negative 50 grams. Mass was negative last night. I have called Stockholm. I have informed them that the University of Mississippi is sending in its application for the Nobel Prize in Physics because we discovered negative mass. Mass is always positive. Oh, I'm getting in one of those moods this morning. So, there are certain things that should just cause your brain to freak out and go, you know what, I'm not going to bother Dr. Eschenberg with negative mass because negative mass is wrong. One of two things has happened. Either A, we've invented new physics, or B, you messed up. I put my money always on B, just to play it safe. We're not going to discover new physics in Physics 223. Just a tip. No, it's not going to happen. All right. Oh, I feel better. In a way, this is therapy for me. Oscillations and pendulums. There are two types of pendulums that we're going to deal with. One is a spring pendulum, and the other one is a simple pendulum. Spring pendulum, they use a spring. You pull the mass down, you let it go, and it goes bouncy, 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 up, down, up, down, up, down, up, down. Ooh, that's kind of weird because there's a little bit of delay. All right.
On the right, what shape is that? Is that like a circle?
Well, I haven't gotten to that yet. Oh, can I? May I talk? May I continue? Thank you. I'm in a playful mood this morning. It's getting weird. Now, the simple pendulum, it's like a grandfather clock. You've got the long arm, you've got the mass at the end of the arm, you pull it to the side, and it goes swing, 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 like swing back and forth, swing, swing, swing. So with simple pendulum, you pull the thing back and forth, and it goes back and forth. With a spring pendulum, you pull it down or push it up, and it goes bouncy, bouncy, bouncy. Why am I so stressful about, or stressing this so much? Because you guys are going to have a lab in, is it next week that you're doing oscillations? Probably. So next week you'll do oscillations. We're getting down to the last few weeks. I think it's oscillations and speed of sound and air, and that's it. The dead week, that's for like makeup labs and stuff. We're not meeting the last week. So enjoy. I know. Thank you. Thank you. In that lab, the last time that I was a TA, oh, and on a side note for TA positions, probability is high that I am going to be a TA again. I will be the TA of the worst sections possible, which are Thursday 5 p.m., Thursday 7 p.m., and I will fill them because I'm awesome. So, and on another side note, thank you very much for filling up the class in record time. For those of you who have not gotten into 214, keep patient, be patient. Also watch for the occasional person who tries to change their lab section and my Ole Miss kicks them out. So I'll tell you who that person is, and so you can send them a gift basket once you grab their class slot. So for spring pendulums, you pull it down and you let it go. An oscillation that whole bouncy, bouncy, bouncy is one oscillation is where it goes from one position up, back to its position, down, and then returns. It makes one cycle. Some people think it's from there to there. No, it's got to go up and down completely in order to be considered one oscillation. For a simple pendulum, oh, I shouldn't. Hold on, let me do another sheet of paper. I've got paper. where it starts on one extreme end, goes down to the bottom, goes to the other extreme end, goes back down to the bottom, and then it goes to its starting place. In a case of a spring pendulum, if you were to plot displacement over, and that's its rest position, and this is time is the horizontal, displacement is the vertical, you get that is its period. The time it takes to go from one extreme to the other and back. If it was a, let's say, simple pendulum, time would be on the horizontal and angle theta would be on the vertical. And so you get this, once again with period. Starts at one extreme, goes to the other, and then comes back.
What does that say? Rest pop, the rest is positive?
Rest position. So you got the displacement, you've got the angle, and you've got period. This is called amplitude. And this is called peak to peak. Amplitude, they shorten to A. Peak to peak, they use P. You can call it whatever you want. Cheeseburger, as long as you say cheeseburger is the peak to peak. I know, cheeseburger. Peak to peak is twice that of amplitude. Now, when I first started teaching, I was like, well, peak to peak's kind of dumb. All it is just twice the amplitude. Or you could even say that amplitude is peak to peak divided by 2. But there is one of the things that you start noticing in physics is it's one thing to write down on a piece of paper and go, well, that's the amplitude, just measure that. How hard is it? Well, if you're in the lab, measuring the amplitude actually is kind of rough because you can tell where this thing peaks out, but figuring out where this middle level is actually kind of difficult and not quite precise. The best way to do it is to measure that distance. Easier to measure. So if you measure the peak to peak, all you got to do is divide by 2, and then you have a much better opportunity, or a more accurate way of determining amplitude. So it doesn't have to be that hard. There are many ways. I mean, this is where there is a difference between the theorists and the experimentalists. Theorists tend to do stuff on the whiteboard. I like the theorists because I could sit here and just wave my hands and stuff. But with experimentalists, you got to get in the mud and get dirty. And in getting dirty, there's some things that you go, determining amplitude's hard. It's inaccurate. I can determine peak to peak quite easily, divide by 2, and I got it. So there are advantageous ways of, it's a lot like when you did the moment of inertia and you had to determine the radius of that axle underneath the thing, the Beck's inertia thing. Well, determining the radius is hard, but determining the diameter is trivial. And what do we know about diameters and radiuses? Radiuses are half the diameter. So you measure the diameter, divide by 2, and go on. This is a practical reason, or a practical reason to do what you're doing in the lab that may be slightly different from doing it on a whiteboard. So with these spring pendulum and simple pendulum, there are the periods, and they have periods. And so for a spring pendulum, and there is a calculus-based way of deriving the periods. We're not going to go into that. But the periods are equations for them. So for a spring pendulum, it's 2 pi square root m over k. Simple pendulum period is 2 pi L over G square rooted. And a lot of times, how do I know it's this and not this? Well, one of the easiest ways to take advantage or to determine this, you play with the units. M is in kilograms. K is in newtons per meter. So let's play with this. That changes to kilograms, meters over newton. A newton is a kilogram meter per second, which leaves me with seconds squared. And all of this is under a square root anyway, and so you get seconds. So it is m over k. For the simple pendulum, yes?
What is K?
K is the spring constant. K comes from the time that we talked about potential energy of a spring, that the potential energy is 1/2 kx squared. That K also comes from Hooke's law. And Hooke's law in vector form, F is negative K x vector. So that's where the K comes from. For simple pendulums, L over G, L is in meters, G is in meters per second squared. Meters cancel, I'm left with seconds squared, and square root of seconds squared is seconds. So the units do check out. Because for the longest time, I was like, is it m over k or k over m? I get confused. Well, just work with the units. And if you were dealing with frequency, which is 1 over period, for the spring, it's 1 over 2 pi k over m. And for the simple, it's 1 over 2 pi G over L. What? Because frequency is the inverse of period. So if you took the inverse of period and period was this, 2 pi becomes 1 over 2 pi, m over k becomes k over m. For simple pendulum, 2 pi becomes 1 over 2 pi for frequency. L over G becomes G over L. Now, one of the things that we need to talk about are the dependencies of periods upon various quantities. If m goes up, period goes up. If k goes up, period comes down. So if you increase the mass on the spring, the period will increase. If you increase the spring constant, the period will decrease. If G increases, no effect. It is mass dependent spring constant dependent and gravity independent. Springs don't care. Yes.
If you held the spring at an angle, would it make a difference?
That would be, that makes it, the physics get different. Right now I'm only considering like it working against gravity or there being no gravity whatsoever.
Okay, but it would change if you held it.
I would have to think about it and describe it in English. I don't think it would. Yes.
Gravity not a constant value. Why would you let gravity?
Well, the thing is, okay, hold on. His question's really bothering me at the moment. If you, all right, oh, and actually, let me tell you, I'm gonna get to you in just a moment. I gotta slam down this question real quick. Remember how I said at the beginning, spring pendulums go bouncy, bouncy, bouncy. Simple pendulums go from side to side. Had you pulled that thing to the side and let go, that spring pendulum would want to contract and expand, but it's being held to the side, so it's going to do both a simple pendulum motion and a spring pendulum motion at the same time. That's a nightmare situation that even grad students start to sweat. So, and actually, the last time I TA'd, there was a group who couldn't get their spring pendulums to work. And I walked up to the desk and I was like, well, show me how you're taking the data, thinking that they would pull the mass down, let go, and it would go bob, 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 up, down. What they did is they pulled that thing to the side, let go, and it went back and forth like this, and it was doing that as well. And then my brain did that derpy derp like it did last night in lab. And I was like, you can't do that, because what you're suggesting is you want to take a spring pendulum and make it behave like a simple pendulum. You can't do that. Well, you can because you just did, but those equations would not apply. You would have to, you'd have to get a Hamiltonian of the situation, and your brain just exploded because you have no idea what a Hamiltonian is. Hamiltonians are equations that deal with this that are far more complex. That's like someone going, why is the person jumping into the 10-meter pool off the 20-meter board? That's harder stuff. Let's ignore that. Keep your floaties on. We're going to be in the kids pool until January. Okay? Does that answer the question? Okay. Now, I haven't forgotten about you yet, Adrian. So with gravity, gravity plays no part in it. It may change the gravity changes how the magnitude of how far the amplitude of how far it goes. With normal G, that thing stretches a little bit, so its displacement is this way and its force is this way. With an increased gravity, the spring force increases as well. So it does affect how far it stretches, but in terms of the oscillation itself, once again, this is where the derivations come into play, and we can't talk about that. It doesn't have any effect. Gravity has no effect on the period. Gravity affects the amplitude. But this is where we come into a word. Uh-oh, I'm standing up, so now I'm going to interact with the class. Someone asked, one of the yielding cousins asked about, use names, now I get everybody's attention. They asked about what's K. And don't worry, I'm not going to talk to them because they've already provided me the material. You, I'm going to talk to. So for K, what is the words describing K? What is it? Don't look at the board, look at me. Serious? Where are you visiting from? ICC? Are having a good time? No one look at her. She gets embarrassed when everybody looks at her. So you're just visiting? Are you thinking about transferring? You're a film student. Why is she in physics class right now? She should be over in film.
Because it's older classes, I don't think she should know.
And is it living up to the hype? Excellent, thank you. All right, I hit the one person who is in the class. Excellent. All right, Beebs. What is K? Spring constant. Second word, constant. So, if I had a spring on the moon and then I brought it down here, does the spring constant value K change? No, because it's a spring constant. If I took it out into space, let's say it was 300 newtons per meter, and I took it into space, what would its spring constant be? 300 newtons per meter. Hence, constant. It doesn't change. Hence the name constant. So, gravity has no effect on K. You could have it on the moon, you could have it on Earth. That spring is going to stretch and contract at with the same values of K. In fact, one of the things that they do is, and this is what we go over in lab, you have a mass, you put on another mass, you put on another mass, and so on, stretching it. Let's say we just do it 4 times. Each of these have their own forces that increase. Because there is an force from gravity pulling down. So the first part of lab, when you do this oscillation lab, you're going to take mass, you're going to put it on, hanging it from whatever it hangs from, and you increase the mass. And what you're going to do is you're going to have in one column you're going to have the mass, in the next column you're going to have like M1G, and in the next column you're going to have the displacement. So you're going to have all those bits of information. And then, let's see, F. Or actually, I know, hold on. Let's do this right. So what you're going to do is, I always got confused with writing graphs. The horizontal is where the independent variable goes. The independent variable in this case is the mass that you hang from the spring. The vertical is the dependent variable. The independent variable in this case will be the force. The vertical will be the dependent variable, which is the displacement. The displacement has to be the dependent variable. It depends on how much mass is hanging from it. You can hang 30 grams of mass off that spring, and you have control over 60 grams. You're the one who has direct control over the mass. You have indirect control over the displacement. Now, the equation is set up, x is 1 over kf, which just comes from kx is equal to f. When you plot this out, the slope is 1 over k. So 1 over slope is the k value. So you take this spring, you hang various masses off of it, you measure the displacement, and that slope that you determine, you invert it, and that is the spring constant. And what you do is you compare K from this part with the K from the following part. Now, in the next part, what you do is you pull the mass down and you let it bob. And you don't let the thing bob once, you let it bob like 20 times. And you record the time that it takes for that thing to bob. And what ends up happening is you can adjust the mass, do all sorts of things. But, oh, you are going to adjust the mass. So you're adjusting the mass, you're letting it bob 20 times, you're recording the time that it takes to do this. You get the period. And what happens is, I guess you can add the force. So the force, which is just the mass times gravity, or actually what I would do, no, take that back, just use mass. And you plot period squared. So there's going to be a period squared in that part too. So why period squared? Well, period is 2 pi square root of m over k. If you double m, you don't quite double period. But if you use t squared, if you double, oh, hold on, get rid of that whole thing. T squared equals 4 pi squared m over k. If you double m here, you double the period squared on the left. If you only had t and m, it would not be, it'd be some weird curve thing. So it's not something that you can easily find the slope of, because the slope's changing. But with t squared versus m, it is a line. And what you end up doing is you rearrange this. Now this particular m is the mass m. But this particular segment is the slope m. So m as a slope is 4 pi squared over k, or k is 4 pi squared over the slope m. And what you're going to determine is, does that k there agree with that k over there? It should. You're using the same spring. What you do with it is your own deal. So that spring will have the same value. Does it agree? Does this procedure K agree with that procedure K? If it does, congratulations, you're done with that part of the lab. Now for the other one, for the simple pendulum, what you're going to do is, let's write it out, T if I increase L, period increases. If I increase G, period decreases. If I increase M, period doesn't change. So it is length dependent It depends on the length of the string. It is gravity dependent. This thing will change its behavior based on where it is on Earth, on the moon. And it is mass independent. So if you change the length of the pendulum, you're going to change the period. If you change the gravity that the pendulum is experiencing, you're going to change the period. However, you could have a mouse at the end of the string, you could have an elephant at the end of the string. The mass is irrelevant. You're going to get the same period. Now, in the experiment, what you're going to do is you adjust L and record T's. So you're going to have L, and you're going to record the number of oscillations and the time and the period, and you're going to get a whole bunch of information. And I think there's a subset of the problem where you have one length of string, you bob it, you determine the period, you change the mass, you bob it again, and you determine that it doesn't change. But the important part is this. T squared is 4 pi squared L over G. And once again, you're going to plot period squared on the vertical, and on the horizontal you're going to plot L, and what's going to happen is you're going to get a list of plots and a straight line. That's not straight, but work with me. Rearranging this, period squared 4 pi squared over GL, you get this equation. This is the slope of the linear line that you fit. So the slope M is 4 pi squared over G, and G is 4 pi squared over M for slope. Not the mass of the object at the end of the string, but the slope itself. And that G should be 9.81 meters per second per second. It's not going to be 10. 10 is whiteboard physics. Yes? Is that how an altimeter works? I don't think so. Not. Yeah, it's not that really noticeable. Let's talk about that later. It's a good question, but not here. I think with an altimeter, they use air pressure difference. I think it's that, rather than changing gravity. I don't think there's a pendulum inside a plane just knocking back and forth. I don't think so. So there you have it. Those are the two simple types of pendulum. Trying to think. Oh, one last thing before we go, and then we'll be ready for all of the stuff. Pendulums are similar to waves. Like if you had a wave in a pool, it looks a lot like the amplitude and stuff that we did earlier, but and if your horizontal is x, rather than t, you're measuring wavelength, and if it is t, then it's measuring period. Lambda, wavelength. Lambda is the distance between peaks or between troughs. Peaks are the high points, troughs are the low points, so that would be lambda as well. Period, it could be from peak to peak or trough to trough. That would be a period as well. And the relationship between all of this is that lambda over t is equal to velocity. You could even say that lambda f is velocity. Now, how does this work together? If you do the units of lambda are in meters, the units of frequency are in inverse seconds, and so that gives you meters per second. And so there will be, there are problems where it's asking for the velocity of a wave, so many bobs up and down over a certain amount of time. And this connects everything through. So what I believe we're now ready to do problem set 10. There's still a few copies left up front if you haven't picked one up. We'll do this problem set tomorrow in tutorial. That's it. See you next week.